there, guys. I'm over here. Today's lesson is graphing radical functions. And before we begin, well, I promise that this will not go past the 30-minute mark, and hopefully less than that. But here we go. We're going to be graphing, and so I want to just kind of revisit some of 7.7 real quick. We recall that we have a function x squared, and this is a function because it passes what we learned in chapter, I believe it was chapter 2, about what makes a function. And we had this little thing called the vertical line test. And so this function passes the vertical line test, which means that if I were to draw any vertical lines through the graph, it would pass the test of only crossing one time. Well, we've also learned in 7.7 that this is the inverse function, plus or minus root x, and this function fails the vertical line test because it crosses twice. And so this is not a function. So then how do we deal with that? How do we talk about graphing a radical function if we just said that it's not a function? Well, that we come here, and again I've graphed the same two functions. One of the things that we can do to kind of force a function, the inverse function, to actually be a function is to do something we call restricting the domain. Restrict domain. So what that means is that we have to choose to not use part of the graph. So, and maybe that'll make more sense once I actually show you how it works. For example, what if we know what the domain is, right? For a well-behaved function, you're looking at this function and we talked about the two problems, division by zero, square roots of negatives, or even roots of negatives, and this has no division in it, and it has no square root in it, so the domain would be something like all reals. But we can actually restrict the domain, which means that even though we know that it's not a problem, since we know this is a problem, the inverse function, we can choose to restrict it. We can choose to erase, so to speak, part of the graph so that it's no longer there. This is only 1/2 of the parabola. And when we do that, we can actually make our domain be x is greater than or equal to 0. So we'll start here at 0, 0, and then we'll use just 1/2 of the parabola. If I do that, then the inverse part of it will be just the top half. So you guys know how this works. And I will go ahead and finish this. The range of this function would be the y values are from 0 on up. So y greater than or equal to 0. And I think that you guys know how this works. We talked about the domain and range being inverted last time. So if this is the inverse function, then we want the range of the regular function to be the domain. So where this says y, we're going to call this x. And then for the range, we're going to call this y. Okay? So all I've done here is to invert the domain and range. And if that's the case, if the domain is for x is greater than 0, that means that we only want from x is 0 on up, which is totally fine. But for the range, we only want y's greater than or equal to 0. So these y's right here are all negative, so they wouldn't count. So again, we erase that. And now, what we're left with does in fact pass the vertical line test, which you will remember from before is how we do this. By the way, I'm really sorry about this, but it looks like I need to change my battery because it is dying here. Really sorry. Hope it doesn't take too long because I don't want this video to get crazy long. Let's hope that this other battery that I have here works, and hopefully we can continue. Sorry about that. That was an unintentional, what do you call it? Dashed line. That should be a solid line there, and it's not working. Come on. Let's see here. Negative, positive. Okay. Is that working? Okay. Let's try that. There we go. Okay, sorry about that. All right, so this function actually does pass the vertical line test. Also, if you wanted to graph this function on the same axis, you could see how it goes through y equals x. So just want to be clear that radical functions are basically the inverse of quadratics, but you have to restrict the domain. You cannot keep both parts of the parabola and then have an inverse function, because I said before, it's going to fail the vertical line test. You can also restrict a different part of it. For example, you can see that the right side of the parabola is inverted with the top half of the square root function. And if you had kept the parabola going this, if you had taken this part of it, this part here, then that would be inverted with the bottom half. Okay? So this black piece is the mirror image of the pink piece. So this left half of the parabola is the bottom half of the square root function. The right half of the parabola is the top half of the square root function. It's important for you to know what the square root function looks like, because today we're going to be graphing it a lot. So you want to know what the graph looks like, and this is what positive square root of x looks like. And if you were graphing negative square root of x, it would be the bottom half of the parabola, and it wouldn't be the top part. Okay, but again, we'll discuss that more as the examples come up. Okay, we also want to talk about cubic functions. We've seen cube roots before, so this is a cubic function, and what I did is I went ahead and picked 3 arbitrary x values, -1, 0, and 1, plug them into the x cubed function to get the y value. So if I take -1 times -1 times -1, I will get -1. 0 times 0 times 0 is 0. 1 times 1 times 1 is 1. So you can see -1 is right here, 0, 0, 1, 1, and I put my graph, and that's what it looks like. Almost like a parabola, but this half, instead of being up here, it's kind of gone down. So your cubic function looks like this. And then, of course, the inverse function would be the cubed root of x. And in this case, there's no plus or minus. We talked about that's only when you have even square roots, so this is an odd root, so not a problem. But you can invert all those values. Now that's interesting, because if you can look here, all these values are the same. -1, -1, 0. So when you invert them, you get the same thing. So you still get the same 3 points. But a cubic, the inverse cubic function is this guy, which is the cube root function. And again, if I were to graph it over here on the same axes, you would see that. And again, it should be pretty clear to you that we have the y equals x going right through the middle. So they're mirror images. So again, your cube root function looks like this, and your square root function looks like the top half here. Okay? So now we're going to talk about vertical and horizontal translations. And by the way, even though this says square root, it's the same for a cube root as well. And I will remind you that we've done this already with quadratics, and we've done them with absolute value. Basically, that if you know what the parent graph looks like, if you have an h or a k, the h is a horizontal shift, and the k is a vertical shift. So if you know what the parent graph looks like, then you can shift the graph left, right, up, down, depending on h and k. So I want to remind you, we've done this already with y equals a times x minus h squared plus k. We had that. And we've even done it with absolute value. And one of the things that you will notice from the previous examples is that the h is always inside of grouping symbols. So in this case, the grouping symbols were the parentheses, and the h is inside. And in this case, the grouping symbols are absolute value bars, and the h is inside. And in this case, the grouping symbol is the radical, which keeps the x minus h inside. And then the k is always outside of that, so your plus k, and your plus k. Now, obviously, we're not going to be doing parabolas and absolute value, so we want to go back to this. And just want you to write this down. It's the same that we've had in the past. Basically, if you have a plus h in here, it means you're going to shift h units to the left. A minus h shifts h units to the right. And then for the vertical, which is the k part, the k shifts at k units up, and the negative k shifts at k units down. All right? So now we're going to do some examples of how all this comes together. And what I want to show you right now as my example is the parent graph, okay? What does the parent graph look like? Well, I can do a t-table really quickly in my head. I know that if x is 0, which is right here, then the square root of 0 is 0. So I can plot the point 0, 0 right here. And if x is 1, then the square root of 1 is 1, and I can plot that right there. And then if x is 2, the square root of 2 is 1.4. So I don't like to use the number 2. The next perfect square that I know of is 4. So I'm going to skip all the way to here's 1, 2, 3, 4. And the square root of 4 I know is 2. And I'm going to use that as my square root function. That is what the square root of x looks like, okay? But right now, we are being asked to graph, the square root of x plus 2. Because there is a k value, the plus 2 there, that means that each of these points that I just drew is going to shift 2 units up. So instead of being here at 0, this point's going to be 2 units up. Okay? And this point that was here at y equals 1 is going to shift 2 units up. So instead it'd be 1, 2. And then the 4, which is at 2, is going to shift 2 units up. 1, 2. And then your graph is going to look like that. Okay, so it's just shifted 2 units up. All right. Also, we have root x minus 1. And that is going to take this black graph and it's going to shift it 1 unit down. So again, these 3 points I just put up here are all going to shift 1 unit down. So let's put some numbers in here. So this is going to go 1 unit down. This is going to go 1 unit down. And this is going to go 1 unit down. And then your graph is going to look like that. And that is how you use translations to graph these two. All right, so now you can try to graph these two functions. One's a minus 3, one's a plus 3. And then I will show you how to graph something that has a horizontal shift. What we just did was a vertical shift. Now you will notice that the plus 3 and the minus 2 is inside the square root. So that means that it's going to shift it left and right, not up and down. Okay, so again, we're going to start with the parent graph. So my parent graph is, again, we're going to go 0, 0, 1, 1, square root of 1 is 1, and we're going to go all the way to 4. And 4 is going to be at 2. So 4, 2. So there's my graph. Same square root function. This time, because this is a plus 3, if you go back to your notes from before, that means we're going to shift the graph 3 units to the left. So that means at this point, instead of being here, it's going to be at -1, -2, -3. We're going to shift it 3 units over. And then this point's going to shift 1, 2, 3 units over. And then this point, which is at the 4, is going to shift 1, 2, 3 units over. And then there's your graph. Okay? Then we're going to have the root x minus 2. And because this is a minus 2, it's going to move 2 units to the right. So again, we take this point here, and I'm going to go 2 units to the right. This point's going to go 1, 2 units to the right. And this point's going to go to 4, 5, 6, 2 units to the right. And you're going to have that graph there. Okay, very simple. So now you can graph those two. And then I will show you how to graph something that has a in front of it. You remember from before that when you had y equals x squared, and if you had y equals 1/2 x squared, the 1/2 kind of made the graph a lot fatter, wider. And if you had something like a 2x squared, it made the graph narrower. So you had like an x squared, this might have been a 1/2 x squared, and a 2x squared would have been skinnier in the inside. A very similar thing will happen with square root functions. So right now we're going to graph 3 of them, root x, which is the parent graph, 1/2 root x, and 2 root x to see how that affects the graph. I kind of want this to be a little bit bigger, so we'll keep going like that. I hope I'm not blocking all of your vision here. There we go. Okay, so root x is the parent graph. So I will go ahead and do that in blue. So again, we are at 0, 0. And we want to have some markings here. 1, 2, 3, 4, 5, 6, 7. We might even want to go a little bit further to 8. And then we're going to go 1, 2, 3, 4, 5, 6, 7, and just a little bit further to 8. And so, again, I'm going to go 0, 0. We know that square root of 1 is 1, so 1, 1. And here's 1, 2, 3, 4. The square root of 4 is 2, so that'll be right here. And even if you go all the way to 9, which would be right about here, the square root of 9 is 3. So 1, 2, 3, we're going to go all the way over here. You would add in another point. So that's kind of what your graph is going to look like. It kind of missed the mark there just a little bit, but that's okay. Now what is 1/2 root x going to look like? Well, it's the same thing as root x, but after you get your value, you have to times it by 1/2. So for example, when I plug in 0, the square root of 0 is still 0, but then 0 times 1/2 is still 0. So I'm still going to have this point here, 0, 0, and I'm going to now do it in green. So this guy is going to be in green. So I get 0, 0 again. And now when I go square root of 1 is 1, I take that 1 times 1/2, and I get 1/2. So instead of it being 1, 1, it's going to be 1, 1/2. So it's going to be right about there in the middle, in between 0 and 1. And same thing happens over here, where x is 4. The square root of 4 is 2, and 2 times 1/2 is 1. So at 4, it's going to be 1. And then at 9, we said that the square root of 9 was 3, and 3 times 1/2 is 1.5. So it's going to be, here's 1.5 right about there. So maybe right around here. And 1.5. It's a little lower than that, sorry. Let's undo that. 1.5 is right about there. Okay, so there is your root x. So you can see that the 1/2 root x kind of made it skinnier, which is interesting because with x squared, the halves make it wider. But because this is like the inverse function, the opposite is true. So when you have a 1/2 or a 1/3 or a 1/4 in front of the root x, it's going to make it skinnier. It's going to make it tighter to the x-axis. Okay, so when I say skinnier, imagine that this is a parabola on its side, right? Pretend. Okay, it's getting tighter to the x-axis the bigger the number on the bottom is. So 1/5 would be even tighter. But of course, we don't graph both parts of the parabola, so we're not really having that. I'm just giving you guys a way of, oops, too much there. I'm just trying to give you guys a way of seeing what's happening there with the graph. Okay, so then you can imagine then after seeing that, 1, 2, 3, 4 here, that 2 root x, you should expect the graph to be over here somewhere, making it wider. Okay, so we'll do that. We'll go through the process here. And again, we put 0, square root of 0, 0, 0 times 2 is still 0, so we're still going to start right here at 0, 0. When I choose 1, the square root of 1 is 1, but 1 times 2 is 2. So now instead of it being 1, 1, it's 1, 2. And you can already start to see its shape getting bigger. 4, square root of 4 is 2, 2 times 2 is 4. So when x is 4, it's going to be 4. So 1, 2, 3, 4. So over here. And then 9, square root of 9 is 3. 3 times 2 is 6. So this is 6 right here, and this is 9. So it's roughly somewhere here. Okay? So there's my graph. So you can see that the pink one is a lot wider, and this is the 2 root x there. Okay? So basically, root x is the blue one. We should probably mark that. This is the root x, the generic one here. And then the 1/2, 1/3, 1/4, the fraction in front makes it skinnier or tighter to the x-axis. And the number in front, 2 or 3 or 4, will make it wider or away from the x-axis. Okay, so then you can graph these two. I wonder what this negative is going to do. We know that, I'm going to give you a hint. I don't want you guys to get too scared, okay? I want you to see what's going to happen. We know that with a normal parabola, this is x squared. So a negative x squared would do this. It'd be upside down, okay? So this is kind of like a parabola. It's on its side, okay? So you could imagine the parabola is kind of doing this kind of thing. It's on its side. So what will happen when you have a negative square root is that it should flip over, just like the parabola is flipped over. But instead of flipping over like this way, it's going to flip to this side. So you're going to get something that looks like this for your graphs, okay? Just so that you know, don't want you guys to be surprised because you have, both of these are negative, but one has no number in front and this one has a 2. So we should expect the 2 to make it wider, but also that the negative would flip it to the other side. So you can try that one on your own. And then here's one where we're putting it all together. You can see that there's like a negative 2 in front. It's got a horizontal shift and a vertical shift. So we're going to graph one that has it all put together. Alrighty then. Here we go. And it's negative, so in case you didn't get the last example, maybe this one will help you out a little bit more. I'm going to start first and foremost by graphing the original function. That's how I like to start. So again, I'm going to say that 0, 0, 1, 1, and 1, 2, 3, 4. Square root of 4 is 2, so 4, 2. Here is my parent graph. Okay, and then I'm going to graph the other one in pink. Okay, but what I need to do is, first I'm going to deal with the shifting thing. The +1 means that I'm going to shift 1 unit to the left, and the -3 means I'm going to shift 3 units down. So this point is going to go 1 unit to the left and 3 units down. Okay? Now remember that the value of y here is 0. Well, what happened if I multiplied that 0 by -2? Absolutely nothing. It would still be 0. So this point is going to be right there. Okay? Then I'm going to get the 1, 1. And remember the y value here is 1. Okay? So when you get the square root of 1 times 2, it should be 2, -2. Okay? So that's important because you'll see what I'm going to do right now. This point is going to shift 1 unit to the left, just like the previous one did, and 3 units down. Okay? This is where it would normally be. But aside from that, it has to be at -2 or times 2. So instead of being here, it's actually going to go 1 further or 2 more further down. So another thing that you can do is if you don't like the way that that's working out, you could always just plug in the number. We know that this is x equal to -1, okay? If we shift this over, this is x equals -1. So what I'm trying to tell you is, if I put -1 into the equation, that's -1 plus 1, which is 0. The square root of 0 is 0, and 0 times -2 is 0, and 0 minus 3 is -3. So if you had a t-table, when x is -1, you would get -3, which is in fact -1, 1, 2, 3. There's my point. Okay, if you plug in 0 into this function, you're going to get 0 plus 1 is 1. The square root of 1 is 1. 1 times -2 is -2, and -2 minus 3 is -5. Okay, so here you have 1, 2, 3, 4, -5, and that's where your other point would be. So here was our first point. There's our next point. What happens when you plug in 1? Okay, well, when x is 1, we get 1, right? I'm sorry, we already did that point. That was this point. Now we're on 4. For 4, you get 2, okay? But again, you can shift it 1 unit over, 3 units down, but you want to double that to 6 units down because of the times 2. So it's going to be way down at -6. But again, if that doesn't make sense, it's okay. Just plug in. The numbers that I'm plugging in are x is 0, because that's the parent graph's point. 0, 1, and 4. So I'm going to plug in, instead of plugging in the 0, because I shifted it over, I'm going to plug in -1. This 1 is going to shift to 0, and this 4 is going to shift to 3. So those are the 3 values that I'm using. So now I'm going to go 3 plus 1 is 4, the square root of 4 is 2, 2 times negative 2 is negative 4, and then negative 4 minus 3 is negative 7. Okay, so we have to go down one more to negative 7. Okay, so when x is 1, you get negative 3, 1, 2, 3, there's that point. When x is 0, you get negative 5, which is right here. And when x is 3, we're going to go all the way down to negative 7, which is right about there. And then you're going to graph, sorry, my shadow's in the way. You're going to graph like that. Okay? And that's what your graph's going to look like. So it's shifted 1 unit over, shifted 3 units down, and this times 2 is going to make it wider than it normally is. So you see it's kind of big and fat as opposed to that one. Okay? So now you can try one right there. Notice that there's like a 1/4 in front. Okay? And then here's this example. And now we're going to graph one that's a cubed root. But again, all of the stuff that we talked about before that pertains to radical functions, to square root functions is the same for cubed root. The plus 3 is 3 units to the left. The minus 1 is 1 unit down. And then the times 2. So with this guy, I'm going to start with the parent graph again. Parent graph. I hope we're doing okay on time here. Otherwise you'll all shoot me. Please don't shoot me. We talked about 0, 0. When x is negative 1, y is negative 1. And then 1, 1. So this graph, this cube root function, looks like this. Okay? Alright. So we're going to do a little t-table here. Okay? This is the parent graph. Okay? Negative 1, 1, 0, 0, 1, 1. Okay? So what I'm going to do is this point is going to shift 3 units to the negative side. So if I start here at negative 1 and I shift it 3 units over, that's negative 1, negative 2, negative 3, negative 4. So I want negative 4 over here. The 0 is going to shift 3 units over, 1, 2, 3, so I'm going to want negative 3. And then the 1 is going to shift 3 units over, 1, 2, 3, and negative 2. So the 3 values that I want to put in my x column are negative 4, negative 3, and negative 2. Okay, then I can get my y value very simply by going, what is negative 4 plus 3? Negative 4 plus 3 is negative 1. The cube root of negative 1 is negative 1. Negative 1 times 2 is negative 2. And negative 2 minus 1 is negative 3. Okay, now we're going to try the negative 3. Negative 3 plus 3 is 0. The cube root of 0 is still 0. And 0 times 2 is still 0. And 0 minus 1 is negative 1. And then we plug in negative 2. So negative 2 plus 3 is 1. The cube root of 1 is 1. 1 times 2 is 2. 2 minus 1 is 1. And now we can plot those points. Negative 4, negative 3. So there's negative 1, negative 2, negative 3. So negative 4, negative 3. Then we have negative 3, negative 1, which is right about here. Negative 3, negative 1. And then we have negative 2 and positive 1. So negative 2, positive 1. Okay? So now we're going to have a function that looks like, oh wow, that's not good. That's kind of bad. Let's start it from this side. It's going to be like that. Okay, so you can see that the 2 here in front made it a lot wider. Instead of it being kind of tight here, it kind of opened it up a little bit. So that is how you graph cube root functions. So now you can try this one on your own. And then our last example is this guy. And what you'll notice about this guy, it's asking us to rewrite it. You'll see that this graph here, this equation, the function, is not in the normal form of x minus h plus k. So we kind of want to rewrite it so that it is in that form, and then thereby making it easy to graph. They're not actually asking us to graph it. They just want us to describe the graph. So what you want to do in these cases is do some factoring. For example, I know that 4 is a factor of 12. So if I take out the 4, I get this. 4 times x is 4x. 4 times negative 3 is negative 12. So I've rewritten it. But I'm not completely done. When you multiply